I believe where we ended was starting chapter 17. And we're now doing addition reactions to polar pi bonds. So that's the sequence, chapter, whatever they put together. So what we're going to write, this doesn't feel right. Is this right? Because didn't we look at that? Okay, so we did. Okay. So this summarizes everything for your addition to polar pi bonds. Chapter 17 is the stupidly strong nucleophiles. Right? That's how we're going to refer to them, because we have strong nucleophiles, and we would know they're strong because negatively charged. They are stupidly strong because they're on atoms that should never be negatively charged, like carbon and hydrogen. Okay? Chapter 18 is then looking at the weak nucleophiles, which is really just our standard strong nucleophiles. Okay? Ketones and aldehydes are important functional groups. We've got a bunch of examples. Everybody asks about why is chemistry important, or organic chemistry important. All of those are carbonyl functional groups. All of those do varying things. We've got our steroids, flavorings, that kind of fun stuff. You can tell how excited I am about that. Nomenclature, aldehydes and ketones. You guys want a little practice? Yeah? Okay. I'll give you a couple minutes. Warm up. Let's go through and name two of these. Let's name this one. And let's name that one. Yeah. Let's do that. So I know it's going to sound a bit broken, but you need to be showing work. Okay? You should be trying to actually write out and identify those pieces. In simpler examples is the perfect time to be showing that work, because that's when you're going to start building up the habits, so that when it becomes more difficult, you actually have that work mindset already set in place. So if you're starting to jump to names and you're right, your argument's going to be, but I'm right, so why do you care? I don't care with simple examples. What I care about is the more complex ones, and if you don't have that process built in, it's not going to work. Okay? So where we start with, let's go with the upper right one. Start by numbering at your highest priority functional group. So 1, 2, 3, 4, 5, 6. Okay? Why start there? Well, the aldehyde is our highest priority functional group. Okay, based off of our list, that carbon needs to be at position 1. Okay? This also helps out because that we now know that those are not part of the main chain. And I could go through a number of those, 1, 2, 3. Okay? Where this becomes helpful is that if I have substituents off of my substituent, I now have a numbering system already written out for it. The time investment it takes to write those down is very, very minimal, and it is absolutely worth identifying it. So if we now break this down through the name, we've got 6 carbons in our main chain, so we're looking at a hex. Okay. The primary, that emphasis was a little weird, our backbone is primarily sp3, so we would specify our hybridization as hexane or hexane. Sorry, we'll specify that as a different color because it's a different aspect of the name. Okay. It is now an aldehyde, so we would drop in at the end that al suffix. Okay. Depending on whose nomenclature rules you want to follow, you should be specifying that it is at the 1 position.
What about
For the far right one, I'm confused. What do you mean double bond? The carbonyl? That is a carbonyl, so that's the aldehyde. So are you referencing the blue sp3? Is that what you're challenging? Okay. I agree. It is kind of confusing there. We're looking at the non-functional group aspect of it. So if there was an alkene in there, that ane becomes ene. Okay. So the ane just changes. That's it. It deletes and becomes ene, which we'll see down with that one in a second. Okay. What's left over? We have a 3-carbon propyl located at position 2. which we know because we've numbered our chain, and we can now put it all together as a 2-propylhexane 1-al. Okay. Do we have a stereocenter? Yes, absolutely do have a stereocenter at position 2. Do we care? No, why not? We haven't specified the location of where those groups are aimed, be they wedged or dashed. So because of that, we don't need to specify it. Okay? I do want you to be aware that there's a stereocenter there. How do we know there's a stereocenter there? 4 different groups. We only see 3 different groups. There's that implied hydrogen. So we've got 4 different groups there. Kind of make sense? Okay. Let's move to that bottom one. Again, we'd go through and do our numbering. Aldehyde, highest priority. This one, interestingly enough, was drawn in an easy fashion because we numbered left to right, okay, in a nice kind of zigzag shape. Okay. So we're looking at a hept for that backbone. If we go through and look at the carbons through the backbone, though, they aren't all sp3 except for our highest priority functional group. We also have that alkene. So instead of calling this a heptan, we'll call it heptene. We have to specify the location of that alkene. It's where the first carbon appears. So it's a hep6ene. Okay? The last part of that name, so if we go through and look at the nomenclature system I've got up here, it says take the E and switch it. That's what we're referencing. We're going to drop that E because there's a higher priority functional group than an alkene. So that E disappears and it needs to become something else. So now what's our higher priority functional group? Well, we have 2 of them. We have an aldehyde, we have an aldehyde and we have an alcohol, which is higher priority. The aldehyde, so this becomes ene 1-al. This more so than the other name, we need to specify that one. Why? We have that alkene floating in that backbone too. Okay, so it's a little bit more clear to specify that number location with our functional group. Make sense? Again, depending, you may or may not see the one for the aldehyde. Why? Aldehydes are very high priority, which means they should start at position 1. Okay? So the numbering system for them tends to get dropped fairly frequently because they can only start a chain.
Is there something on the floor?
Yeah, I keep stepping on a pencil. I just moved it. Okay. What are our substituents? We have a methyl, which I just circled. And okay, we have an alcohol, which we could call OL for alcohol, but there's a higher priority functional group, so what happens? We reference it as our parentheses, a hydroxy. Okay, which one comes first? Hydroxy, because alphabet H comes before M. 4-hydroxy, and I'm going to run out of space here, 4-methyl hept6ene 1-al. Do I need to specify E and Z?
Yes. Oh, well, no, because there's 2.
No, because?
Is it because there's 2 hydrogens at the end of the...
I sort of accept the answer of because there's 2 hydrogens at the end. What does it mean if there's 2 hydrogens at the end?
It's mono-substitute.
Can you have E versus Z? No, E and Z means you have to be able to distinguish both halves. If they're both hydrogens, I can't distinguish them, which means E and Z is a useless system. Right? E and Z allows me to differentiate if that bond rotated. If I can't tell it rotated, then don't use it. Do I have a need for R and S? Yes, because? I do have a stereocenter at 4, and I think you were saying no? Why? No, you weren't saying no? It's not specified again, so we don't have to specify the R and S. Okay? We would need to see those wedges and dashes, or at least a wedge or dash to deal with that RNS. Make sense? We good? Cool. So, where's our chemistry in the carbonyl? At the carbon. Okay, why is that carbon reactive? Why is it partially positive? Okay, we have that polar pi bond. Okay, this is different from our alkene because that pi bond is now going to be drawn towards the oxygen. Why? A large difference in electronegativity. That makes the carbon partially positive, which then makes it an electrophile, which would also mean, if we break that down out of the definition of or break it into the definition for an electrophile, an electron acceptor. Well, if the oxygen just accepted those electrons, what happened to the oxygen? Okay. It would be partially negative. This would make it a nucleophile, and thereby an electron donor. Okay. What other things can donate electrons other than nucleophiles? Bases. Okay. So all of those reactivities are available to us around that carbonyl. Additionally, what else do we have floating with that we might want to think about from that last lecture? Maybe it's helpful if I do this. That hydrogen located at the alpha position to our carbonyl is acidic. Okay. Why was it acidic? There's resonance stabilization of the conjugate base. Okay? At this point in the game, we're going to kind of ignore the acidity of that hydrogen for the most part. Okay? And we're going to focus on our reactivities up here, either the carbon electrophile or the oxygen nucleophile base. To act as a nucleophile, that oxygen must share electrons with something embedded inside a structure. Okay? How likely do you think that will be, and why?
Because oxygen doesn't like to share electrons.
Okay? Doesn't like to share its electrons. Okay? It already has 2 bonds. To pick up a third bond isn't going to be the greatest thing in the world. Okay? To act as a base, to accept a hydrogen, it could just as easily do that. That's also accepting a third bond. Given the choice, nucleophile or base, which one do you think is more likely?
Base.
Why?
Because it has electrons to form that bond.
Doesn't a nucleophile have that? So I saw a nod there. So you're agreeing with that statement? Nucleophile and base.
I'd say base.
Why?
Because hydrogen is very unstable.
It's a possibility.
If you're talking about something like reacting with something like this, you're comparatively, what's it going to hit first, and what's going to be most reactive first is H+.
Because?
Because H+ is size.
Someone mumbled it over here. Sterics. Okay. A size argument. That hydrogen is going to be a lot easier to place on the structure because there's a bunch of bulk behind that oxygen. It's going to make it sterically more difficult to act as a nucleophile. That does not mean it can't. Okay? And there are reactions that it does act as a nucleophile, but it is very limited as a nucleophile. Which means we're really looking at 2 definitions. It's either acting as a base for our carbonyl or it's acting as an electrophile. Which of those chemistries do you think is going to be most useful?
The electrophile.
Why?
Because we're doing the nucleophilic addition.
Okay, so one option, we are reacting these with nucleophile. So you're taking advantage of the context of the chapter is nucleophilic addition. We're adding a nucleophile. Where should the nucleophile go? Probably to the electrophile. Okay, so that's good reasoning. What else you got?
It's carbon, and we're doing organic chemistry, which is based on carbon.
Okay. It's an organic chemistry class. We're concerned about the reactions of carbon. This isn't acid-base class. We're not doing just adding hydrogens and removing hydrogens. Okay. That doesn't mean it won't happen, but the addition of hydrogens or the removal of hydrogens are ultimately done to make carbon more or less reactive. Okay. So our focus needs to be on the carbon acting as an electrophile. Kind of make sense? Okay. So, what are all our nucleophiles? Chapter 17. We're going to start with hydride. Then we'll move through carbon as a Grignard, carbon as acetylide. We'll do very fast. Carbon is Wittig, carbon is Gilman. Anybody notice any issues potentially with all of our carbon ones? Which one of those carbon ones doesn't belong? Let's try that. Carbon ones doesn't belong. What functional group is a Grignard? Have you heard of the Grignard functional group?
Is it an acid base?
I didn't ask for a reaction. What functional group? So a functional group, carbonyl, ketone, aldehyde, alkyne. What functional group is a Grignard?
There isn't.
There isn't. What functional group is a Wittig? Wittig, for those of you that are wondering, is the W, spelled Wittig. I think it's German.
It doesn't exist.
It doesn't exist. Gilman?
Doesn't exist.
Doesn't exist. Acetylide?
Does exist.
Acetylene. It's referencing the functional group of an alkyne. Okay? That one doesn't belong. So why is that one so different than the others? Well, what do the others all have in common? Instead of calling them by the functional group, we're calling them for somebody's name because
it's really hard to get anything else.
It's hard to get a negative carbon. Okay? So those people were able to make a nucleophilic carbon to react with our electrophilic carbonyl. Okay? That's why a name is associated with them. So their chemistries are a little bit bizarre and out there. Okay? Yeah?
Why is the acetylide? Is it just the electronegativity of the CH bond? I mean the sp hybrid?
That hydrogen turns out to be fairly acidic and can be removed with kind of a mild, stupidly strong base, the amide, LDA, can remove that hydrogen. The pKa, because of the high increase in electronegativity of that carbon due to hybridization, makes that hydrogen acidic. If the hydrogen's acidic, we pull that off, and what do we have?
A negative charge there.
A negative carbon that can now react. Okay? So that chemistry was relatively well known early on because it centered on simple acid-base chemistry. Okay? The other ones aren't quite so simple. Okay? Chapter 18 is looking at weak nucleophiles. Okay? Least favorite right there, just for the record. Okay? Oxygen, not particularly happy with either, but the oxygen nucleophile, virtually everything we look at has a direct application to biochemistry. Okay? Just as a heads up. Yes?
What's the nitrogen? Why do you hate it and why is it not useful?
We'll see it when we get there. I didn't say it wasn't useful. It's very useful. I just don't like it. Why? The varied abilities of the nitrogen, particularly at acidic pHs. Okay, so we're going to start our focus with our hydride nucleophiles. Okay? Before we do that, there's our big summary. It's all up there. Okay? So you should be able to go through, pick out those pieces. If you haven't started memorizing reactions, note cards, there you go. Put those on note cards so you can start nailing them down. Okay? So, hydrogen nucleophiles. How do we get a hydrogen nucleophile? H-. We see an H-.
No, you need an ionic compound.
We would need an ionic compound. So what's the easiest ion that we could attach to that negative hydride?
Sodium.
Sodium. And we get NaH. Cool. We have a negative hydride. Is that a nucleophile? No. That one was exclusively a base, and that was solubility. Okay? It's ultimately solubility reasons that prevent that hydride from acting as a hydride. Okay? So it is exceptionally reactive. It needs something to stabilize it. Okay? Have we seen hydride with something else that didn't act as a base? What are we looking at down there? Looks like a reaction. That looks like what kind of a reaction? An addition. Which kind of addition? Electrophilic addition. Using what? What did we add to that structure? We added OH. Mustafa was right, because it's not just OH. We also added hydrogen. So we added effectively what we would have said maybe is H plus and OH minus. If we ran that reaction with those reagents, where would they have gone?
Opposite.
H plus and OH minus would have actually produced this product. How did we get them to go the other direction? We need a different reagent. Good fishing. What do you got?
BH4THF.
BH3 and THF.
Yeah.
Okay. Does not get you that product. Yep, really. What does it get you? It gets you this. So it does add the hydrogen correctly, but it places the boron out there.
Oh, and then you need H2O2.
Then you need,
OH.
damn it, I picked the wrong one. We'll fix it in a second. H2O2, OH minus. Of course I picked the freaking wrong one. So now you're like, oh yeah, that was a good review. That didn't add hydride at all. You're right. Sorry. Let me try that again. Okay, now I fixed it. What did we add?
OH and H.
OH and H. If we tried the same process of just adding H plus and OH minus, what do we get?
That product.
We get that one. Why?
Methyl shift.
We would get a methyl shift. We add the hydrogen, we form a carbocation at a secondary position. A methyl shift causes a rearrangement to get the carbocation at the tertiary position. We get the OH. Didn't want that. Okay? That's review. How do we get that to happen without the rearrangement?
HGOAC.
We would need HGOAC 2 and H2O, which is close because that gets us OH and HGOAC out here. How do we get rid of the mercury? You need BH4, okay, officially sodium borohydride. All right, vaguely remember? Okay, first semester, first unit, or second semester, first unit. What did this reagent do? Sodium borohydride.
It broke your 3-membered ring.
Nope, 3-membered ring was already gone. What's that? Removed the mercury somehow. Remember, the mercury had to donate electrons into this. It's a catalyst. It takes those electrons back. So what would need to come in to stabilize that forming carbocation? Because that's a bad carbocation.
Hydrogen.
I would need a negatively charged species like hydrogen. If hydrogen's negative, it is when we connect it to boron. When we draw out the Lewis structure, we get that negative charge. Which one's more electronegative, boron or hydrogen? Hydrogen. Hydrogen takes those electrons and reacts. What did we just use? Hydride. We now have a hydride reagent, a hydride nucleophile. We didn't discuss the mechanism with the mercury because the mercury does just weird, goofy stuff. We didn't want to deal with it. Okay? Now we get to deal with it, sort of. Okay? So we need to stabilize it. This is where the boron reagent is great, because if I look at just the boron, its happy Lewis structure is that, BH3. What's the problem with that boron? It's missing its octet. What's its hybridization? sp2. There's only 3 groups of electrons, which means what's left over? An empty p orbital. What could we put in that horribly drawn empty p orbital? Electrons from a hydride. That creates a strong enough bond between the boron and the hydride that it's now stabilized for long enough that the hydride can now get out and react as a nucleophile. The boron helps to deal with that intermediate transfer of electrons, and it makes the reagent last for a little bit. Okay? Did we have to pick boron?
No.
What did we need to have? We needed a place to put electrons, right? We needed an empty p orbital. Are there other elements that have empty p orbitals?
Yeah, a bunch of phosphorus.
Phosphorus does not have empty p orbitals. Phosphorus is fully saturated. Sulfur has too many electrons. Aluminum? Why aluminum?
Because it's in the same period.
In the exact same, not period, family or group. Remember all the way back to 151, chemistry follows groups. The chemistry of aluminum, boron, for that matter, gallium, indium, and that's not titanium. And I was going to call it tellurium, but it's not tellurium either. TL. Okay? Thallium? Maybe it's thallium. Okay. All of those carry the same electron configuration. They all have the ability to drop those electrons in from a hydride. Okay? So they could all theoretically be used to stabilize this. Okay? Why theoretically? Well, let's move to aluminum. There's our same goofy looking p orbital. What's the difference between those? What do you mean?
Aluminum is much bigger.
Aluminum is much bigger, which means where's that p orbital? Holding those electrons. Much further from the nucleus, which means that hydride is now less stabilized by the aluminum, which means that hydride is now more reactive. When we look at these two reagents, borohydride versus aluminum hydride, the aluminum hydride is much, much more reactive. If we try to go up to gallium, what happens? Gallium becomes
Bigger.
even larger, which means the gallium hydride is even more reactive, so much more so that we don't use it in organic chemistry. Okay? So we have 2 hydrogen nucleophiles. They're borohydride or aluminum hydride. Okay? So let's go through and take a come back here. We got 2 reactions here. One's with borohydride, one's with aluminum hydride. What differences do you notice?
One's in acidic conditions, one's not.
Okay. One's in acidic conditions. Which one's in acidic conditions? The aluminum hydride is in acidic conditions. Does everybody agree with that? Okay, you're backtracking. Why?
It's in the second step.
It's a secondary step. Okay? Which is a difference. The first one, our borohydride is 1 step. The aluminum hydride is 2 steps. Okay? What else do you see?
You get a better mix off of
NaBH4, you get a better yield, slightly, but it's
So we could look at the yield. We get a slightly different yield.
You also have to use weird solvents.
The second one, we have to use more complex solvents than in the first one.
Is NaBH4 soluble in water?
So we could reference solubility. It's going to be a little bit of an odd statement, and we'll address why in a second. They are both soluble in water. So why not use lithium aluminum hydride in water?
It's reactive enough to react with the water.
The lithium aluminum hydride has a hydride that's much more reactive. What does hydride potentially react as? A nucleophile or a base. What does water have? Acidic hydrogens. The lithium aluminum hydride is so reactive that it must run a reaction in ether, which does not have acidic hydrogens. Okay? How do we put the last hydrogen on then?
Acid workup.
That's why we have the second step of adding the acid. Because if we run our reaction, all we're really saying is that hydride as a negative comes in, attacks, breaks the pi bond, and we'd have our structure. Negative charge on the oxygen. To get the final alcohol, I have to protonate it. In the case of the borohydride, where do I get that positive hydrogen?
The water.
From the water. Where do I get it in the lithium aluminum hydride? I have to do an acid workup because there is no acidic hydrogen in the reaction itself. If there was, what happens? The lithium aluminum hydride does an acid-base reaction, not a nucleophilic addition. Okay? This ties back to the reactivity differences between the two of them. Lithium aluminum hydride is much more reactive than our sodium borohydride. Yes?
You also have to reflux it.
There's a reference on the reflux there, which probably has to do with the temperature of your ether. If you're talking about refluxing ether, what's the boiling point for ether?
Fairly low.
It's like 30 degrees. THF, 70 degrees. So you mean you breathed on it? Yeah, so yes, it says reflux, but it's not that strenuous. Okay?
You still have to do the 70 though. It's more.
Yeah, it's more glassware, yeah. Okay? So we have those two different reagents. At this stage in the game, we don't really discuss the differences beyond that they are different. Why? We're only talking about nucleophilic addition. And within our nucleophilic additions, both these reagents will do the same thing. It's only when we move into the next unit that they start to differentiate. Okay? So, let's address some of those differences between these. We already addressed the size difference between the boron and the aluminum. Everybody was okay with that? Cool. Aluminum's bigger, hydrogen's further away, makes that hydride much more reactive. What else? What's that? Okay, so why is it faster? So one of those reasons is the aluminum is larger. What else is the difference between lithium aluminum hydride and sodium borohydride? We've got lithium versus sodium. Okay? Those are spectator ions. What do spectator ions do? Spectate. So nothing, except in organic chemistry. What are they going to interact with?
Charge.
What charge?
Any charge in the system.
They won't react with positive charges, so I don't quite accept that. They could be using to help stabilize the hydride. Okay, that's useful. That's talking about that reagent. Where else could they interact? And particularly if you're concerned about where reactivity is, it might be useful to draw a Lewis structure. In that Lewis structure, what do we notice?
Negatively charged oxygen.
A negatively charged oxygen. Where could the lithium or the sodium attract? to that negatively charged oxygen. Why is that a big deal?
You help stabilize the negative charge on that oxygen.
We would stabilize the negative oxygen. If the oxygen becomes stable as a negative, what becomes more positive? The carbon as an electrophile. Okay? Lithium versus sodium. What's the difference between those? Size. What does that size say?
Sodium is bigger than lithium.
If sodium is bigger, what happens to the interaction between the oxygen and the sodium?
It's weaker.
It becomes weaker, which means the oxygen is
Less stable.
less stable. If the oxygen is less stable, what is it doing to that electrophilic carbon?
Making it less electrophilic.
Making it less reactive. The sodium can be used to slow the reaction. If we look at the lithium aluminum hydride, there are two things going for its superreactivity. A small counterion, the lithium, and a very large aluminum to stabilize the hydride. It's the combination of both those pieces that changes the reactivity of those reagents. Okay? How much so is it? Maybe I want a slightly more active reagent, hydride, than sodium borohydride, but I don't want it to be active as lithium aluminum hydride. What could I do?
Make lithium borohydride.
Make lithium borohydride. Does it change its reactivity? Yes. Okay. The collection of your hydride nucleophiles, there are tons of them. Okay? And all they've done is modified the ions behind them. Okay? So you can have magnesiums, lithiums, potassiums. All of those change the activity of that hydride nucleophile. We could also go through and instead of those being hydrogens, we can make them carbons. It's still a hydride that's reactive. What's the point of that carbon structure out there? Nitrile, yeah. I don't care about what the structure is. What would be a potential point of that? To dampen the reactivity or make it more active. Okay? That's the point of modifying the outside of that structure. We could go through and instead of doing a nitrile, I could do something like that. What does that start to suggest? What might be at play if we picked a structure like that?
It's bulkier.
It's bulkier, which means
It's less likely to act.
sterics are going to start to come into play. That reagent's chemistry is now going to decrease because we're going to have a steric repulsion. Okay? The key to remember behind these reagents is not that it has to be AlH4 or BH4. The key is to recognize that we've maximized, put extra electrons beyond the happy state of our aluminum and boron, and that we have a hydrogen there that could potentially be shuttled out as a hydride. All the modifications we're doing behind it just tweak its chemistry. Focus on the primary aspect behind them. That will get you through it.
Why doesn't that, say what you've got up there, carbon's more electronegative than hydrogen? Why doesn't carbon only fight and use that?
It has something to do with that bond connection between our aluminum and our carbon. That bond becomes a little bit stronger than the aluminum to hydrogen bond. And so it can eject the hydrogen better.
Why is that?
I don't know. That's all I'll say. I don't know.
Okay,
It does.
fair enough.
Okay? So at this stage, one of the other things we can look at is our solvent choice. Okay? If we use aluminum hydride, that hydrogen is the hydride is much more basic and it will react with our protic solvents. The borohydride will still do it, but it does it at a much slower rate. So much slower that what can now compete with it? The nucleophilic addition. Okay? Aluminum hydride is a reagent that when you measure it out, you have to do it very quickly because each of those hydrides can react, and it will react with hydrogen found in the air. Okay? And it will start producing hydrogen gas pretty much immediately. Okay? Why does that become problematic? There's two big issues. I'll get rid of the easy one. We have flammable hydrogen gas. That's a bad thing.
If you've got enough of it, you can suffocate because you don't.
That's still saying hydrogen's bad, not the hydrogen gas. What's the other issue? You're losing reactant. Why is that a big deal? When you mix things together, you're going to mix things in an appropriate ratio, like a 1-to-1 ratio. Okay? If as soon as you start weighing it out, it's no longer what you think it is your 1-to-1 ratio there? No. Okay? That's going to change the reactivity. Okay? With lithium aluminum hydride and sodium borohydride, they have an extra thing going for them. That extra thing going for them is how many hydrides are there? 4. Okay. Oxygen from the solvent will interact with that center atom, okay, to make the other hydrides be accessible. So each of those reagents has 4 reactive hydrides. Okay, so if you're looking at limiting reactants, they become real fun to deal with. Okay. So nucleophilic additions. Let's take a look at these nucleophiles. Electrophiles. Would we expect them to all have the same reactivity?
No.
Why not?
Because they're not the same.
Yeah.
They're not the same structure. Okay. What makes them the same?
The carbonyl.
We have that carbonyl carbon. Which of these would I expect to be the most reactive?
Your aldehydes.
Okay. Which is a fun question that usually stumps people. Okay. Really, that question is a bit complicated because there's a lot of structures up there. When we're asking for the most reactive one, we're asking you to pick 2. Which 2? Doesn't matter. Pick 2. So I heard the reference to an aldehyde. Which aldehyde? This one or this one?
The one on the left.
One on the left. Okay. So let's throw in the other one. Why is the blue aldehyde more reactive than the red aldehyde?
I don't think it is.
When you do the resonance, you're going to get a primary versus a zeroary carbocation.
There's an argument. We've got a carbocation on a primary carbon. It's not even technically primary, it's zeroary there. Or we have a carbocation on a primary. Which one's more stable?
Primary carbocation.
The primary is more stable than the zeroary. Neither of them are stable. Right? So they would both be reactive, but that's not the question being asked. Which one is more reactive? So we could do an electronic argument. I had a feeling you were going to go with a different argument. What's your different argument?
The accessibility of the electrophilic carbon.
Okay. What is the difference between these? R versus H. What is that R?
Something.
Carbons. Those carbons have electrons. If this is to react with a nucleophile, what was a nucleophile? What's a nucleophile?
An electron donor.
An electron donor. If a nucleophile tries to come in, what's it going to encounter?
Electrons.
Electrons, which means
Repulsion.
repulses away. Our blue one's more active. Okay. That blue one is suspiciously in the middle of all of these. Anybody getting a feeling that might be a little bit weird to have the most reactive thing in the middle of a sequence of structures?
No. Because you might be trying to trick us.
Could be trying to trick you, yep. So let's compare it, because it's easier to go this way, right? What does this one got going for it?
The electrophilic carbon is more positive.
Why is it more positive now?
Your inductive effect.
We have an inductive effect withdrawing electrons. Okay? So we're still using that same sequencing. The acid or the acyl group here is more active than our aldehyde. Okay, we have an inductive withdrawing effect. Okay? You need to be using those same rules all the way through. What were those rules? Charge. Size someone else?
Resonance.
Nope. Size. Electronegativity. Resonance. Induction. Okay? And then we run into the, oh crap, I've got a bunch of different things I've got to deal with. Okay? Usually like substitution effects or hybridization. Okay? We get a big inductive withdrawing effect out with our chloride. That makes that reagent much more reactive. Okay? Why are we not talking about the acyl chloride? What else could the chloride do? It could leave. If it leaves, this would be a nucleophilic addition followed by eliminating something from the structure. Unit 3. Okay? So that's only on there so that we can discuss something about the reactivity behind these. BH4 does all of those fairly well. Lithium aluminum hydride will go out and do the nitrile. Okay? That nitrile is significantly more stable. Right? And so the sodium borohydride can't react with it. Okay? Why would it be more stable? Let's just throw that out there. I'm kind of making stuff up, by the way, for those of you wondering. Yes?
Carbon there is fairly electronegative.
Why is it electronegative?
Because of the hybridization effects. It's a sp hybridized.
We're looking
S characteristic.
higher S characteristics, which would make the difference in electronegativity between those much smaller. Less difference in electronegativity means smaller positive charge. Smaller positive charge means
More stable.
more stable, so less reactive.
It's
Okay?
also nitrogen less
Nitrogen versus, say,
oxygen.
oxygen, our difference there, electronegativity. The oxygen is more electronegative, making our carbon more positive. Interesting. We used electronegativity. Fascinating. We can use the exact same rule set. We just apply it to a different situation. Okay? So, preview into chapter 20. This is where we start adding in other functional groups. Notice there's the acyl chloride, the far right. We also have esters. What does both the ester and the acyl chloride have in common?
Induction.
Kind of an induction, particularly in comparison out to what we're looking at.
There's extra electrons in those.
Yeah, keep going.
So you could have
For instance, we said the chloride could act as a leaving group. We had Cl minus, right?
yes.
Could you get O minus? Depending on conditions, yeah. How about CH3 minus? Not really. In this chapter, we aren't looking at leaving groups connected to carbonyls. Okay, so nothing leaves. Leave it all attached. We just add something and we deal with it. Make sense? When we move into chapter 20, we will add something and then eject something. Just considering that, which of these do you think would be more reactive, the chloride or the ester?
Chloride.
Chloride, because
It's better.
the leaving group is better than that one. Make sense? We're just applying the same rules behind each of these pieces. Okay, so here's some practice. Yep, go through and do these, see what you come up with. If you got questions, raise your hand. So we'll quickly go through these. Okay. For the first part, typically what happens, the student would go through and say, oh, okay, these were silly. All we do is just add the hydrogen, we add the OH, then we do the next one, and we get the exact same result. That's kind of weird. That's because step 1, 2 was missing from the first one, which means what happened in the first one? So, depending on the question, you may very well get it written out as nothing. I would not be surprised if you saw something like this, followed by this. Let's do that. And then a third answer, fourth answer, right? 4 possible answers. What is the ACS fishing for?
Memorization.
Did you just memorize the raw sequence of those reagents and circle the wrong answer? Okay. Remember, we have to be aware of the conditions. That is not shown as 2 steps, which means it's under acidic conditions, which means the lithium aluminum hydride and the dilute HCl react with each other, and nothing happens. How else could it be written? No reaction. It's a bit blatant. You're like, where'd all the carbons go? Why would you just get H2? They're just referencing the other product that happened to not be carbon. H2 is a product of that reaction. The hydride reacts with the acid to form H2. Okay? So, variety of ways that could get put out as a multiple choice question. You got to read a little bit carefully, particularly if you look at something and you're like, why is that one structure so drastically different from all the others? Okay? So if you see something like that, pause and consider it a little bit closer. Okay? The next one, I'm just going to draw a pH for that phenyl ring. We'd get our OH, nothing fancy. The next one, what do we get? We're being asked to go backwards here. So the sodium borohydride reacts with a carbonyl, and only a carbonyl. The rest of the structure, okay, gets drawn very sloppily, but it's there. Make sense?
The methanol is just there to...
The methanol is there as a solvent. It's also there because the methanol is supplying that hydrogen, the end.
Gotcha.
That hydrogen comes from your methanol.
There's solvent in your base.
Yeah, solvent in your acid.
That's all, yeah.
Okay. So, our carbon nucleophiles. Let's see what you guys come up with. How can we get carbon nucleophiles? What do you remember? What's that? What? I can't hear what you're saying. Carbene? Okay. Fair enough, a carbene. I hadn't considered that one, but that's fair. What else?
Ions?
How do you get the ion? Yes. Carbon nucleophile is a negatively charged carbon. How do we get a negatively charged carbon?
Take something away from it.
Okay, like, name a reaction where you've seen a negatively charged carbon. What's that? Grignard. I don't want that one. We haven't talked about that. Try again. Say Gilman, I dare you.
Gilman.
I don't want that one either.
So why did you dare us? We did it last class.
Enolates?
Yeah.
Enolates are negative carbons. Okay. We also talked about the acetylide really, really briefly, and I know that was today. Okay. So those are kind of the big ones we've seen before. They don't show up that frequently. Okay. So these are not easy reactions to run. Okay. Carbon is not very electronegative, and it's very small. Okay. When we actually push into this, we have to find a way for the carbon to become negative, which means it needs to be bonded to something that is less electronegative than it. Okay? So in the case of our carbenes, we're not going to do carbenes. Sorry, I'm just crossing those out. Those are too complicated for this. In the case of our enolates, how did we get that carbon to become negative? What did we do? We pulled off a hydrogen. Is hydrogen less electronegative than carbon?
Yes.
Yes, that's one of the reasons why it works. That electronegativity difference is so close, though, that it's not easy to do. not only do we have to use a strong base, but we also have to have the carbonyl next to it. Okay? What else could we do? We could remove the acidic hydrogen from acetylide or acetylene to make acetylide. So we're again removing a hydrogen. Is that easy to do? No, in fact, it's harder than the enolate. Okay? The pKa for acetylene is about 25. The pKa for our enolate is 16. Okay? So the enolate is significantly more acidic than the acetylene. Okay? But in all of those cases, we had a non-electronegative element or a lower electronegativity element bonded to our carbon. So what could we, let's just theorize, what could I possibly bond to this carbon to make that carbon partially negative? Sodium, right? Large difference in electronegativity, that would be a good deal, except sodium doesn't do a good job stabilizing that negative. Right? So we would need to find metals that are capable of stabilizing the negative carbon. Okay? And to get that carbon into a position where it can become negative. That lies the challenge. Okay? So, where do we start? We take an alkyl halide, so RBr. What's the charge on our alkyl portion? That R is now our carbon. What's the charge on that carbon? Okay, partially positive, be it with they're both bromine. Okay, if I now add magnesium or lithium metal, okay, what is special about both of those materials? Or different about both of those materials?
Valency.
What about their valency? Yeah.
Magnesium has 2, lithium has 1.
Magnesium has 2 electrons, lithium has 1. Do either of those metals keep their electrons typically?
Yeah.
No, they very commonly get rid of them. Okay? And what will happen is an all sorts of fun type of reaction. We will get a single electron going to the carbon and a single electron being shared out. So we will get a carbon radical followed by a bond between the magnesium and the bromine. And then we get a magnesium radical. What happens now? They're unstable. So what do? They react to form R, Mg, Br. What's the charge on bromine? Typically? -1. What's the charge on magnesium? What must the charge be on the carbon? -1. What did we just find? There's our nucleophilic carbon. Okay? It is the insertion of that metal into that bond that stabilizes it enough to give us our Grignard reagent. That is known as a single electron transfer pathway, also known as a set mechanism. You're not responsible for the set mechanism. Okay? The lithium reagent does virtually the same thing, okay? Except it does it faster. Why? Lithium is that much more reactive than our magnesium.
How dangerous is that?
Well, if you were in lab today, you would know.
Ouch.
Okay. The Grignard reagent isn't that big of a deal. It is very reactive. Because why? Why would a negative carbon be a potential reaction hazard?
I was more talking about the lithium. I know, like, when you put lithium in water.
Lithium into water, you're effectively doing the same kind of reaction. It is very violent.
Okay. You just have to be small amounts.
Small amounts, you would control it, yeah, with the lithium. We're going to do the magnesium. Once we've formed the negative carbon, what could happen?
Could react with the air.
Could react with air. What's in the air?
Oh, water vapor.
Water vapor. What's that negative reacting with? reacting with the hydrogen in what kind of a reaction? An acid-base reaction. Okay? The Grignard reagent is an exceptionally good base as well as a nucleophile. Okay? Which means when we run the reaction, we have to really limit the presence of acidic hydrogens. Okay? If there's anything acidic, we get an acid-base reaction. And what happened to my Grignard? Turned into just an alkane. Where did my chemistry start? An alkyl halide. Did I have chemistry at that carbon available? What was the charge on the carbon to begin with? A partial positive. Did I have chemistry? Yeah, I had a partial charge. My Grignard became partially negative. I changed the charge on our atom. That change of charge, for whatever reason, shows up later in the semester, and it's called an Umpelung reaction. Welcome to Willy Wonka. Okay? It's referencing the change in charge. The end result, if we do an acid-base reaction, what happened to my charge? I neutralized it. Okay? Which really sucks. It's like, I'm going to go through to make this super reactive thing, and I end with shit. Okay? So we have to be a little bit careful with our reagents to make sure we don't get those unwanted acid-base reactions. Okay? So, named after the scientist that discovered it, Victor Grignard. Okay? It's rare because it's hard to get a negative carbon. It's useful because it's hard to get a negative carbon. Okay? Why is it tricky? It's a negative carbon. Okay? So it all centers on that reactivity and now just applying it out. Okay? So we have this good, strong nucleophile. We could theoretically use it in substitution reactions. The problem with substitution reactions is we have great leaving groups and then acidic hydrogens, which could do an elimination. Okay? So they aren't the best for just standard substitution. They're much better for our nucleophilic addition reactions. Okay? Which came up a bit fast there. We'll deal with it. What's the difference between those three reactions? What's that? What do you mean reactivity? The first one is a super reactive. Super reactive what? Nucleophile? We said carbon negative, super reactive. Second one has the same nucleophile. So I don't understand. What are you talking about? What's reactive? When we look at the electrophile, we're changing the identity of the electrophile in each of these reactions. That top one is known as formaldehyde. There is nothing to stabilize that carbon or sterically block to shield it from a nucleophilic attack, which means that one reacts very, very fast. Okay? We go to the next one down. We have an extra R group. What can that R group do? It can donate electron density in to stabilize that carbonyl. If the carbonyl becomes stabilized, it becomes less reactive. We move to the bottom one. It's as substituted as it can get. So the speed of our reaction will change with each of these. Okay? What else could we identify here as a pattern that might be useful for us?
The more substituted, the slower it goes.
Okay, so we can look at speed, but speed wasn't listed up here. Speed was something that you guys hypothesized. What did we end with?
The same thing.
We ended with the same thing.
Well, it's attached to the same place. So
We ended with an alcohol, right? So all three of them, we just ended up with an alcohol. Nothing different about them. They were just the same alcohol.
now you have
Functional groups on
ethanol.
We have a tertiary alcohol. We have a secondary alcohol. We have a primary alcohol. Okay? So you could look at your end alcohol and be like, what kind of functional group should I start with? A primary alcohol has to come from formaldehyde. Okay? A secondary alcohol would come from an aldehyde. A tertiary alcohol comes from a ketone. Okay? So recognizing those patterns, you could go through and memorize Grignard, ketone, tertiary alcohol, which my answer is tertiary. Okay? So what I'm trying to do is point out those places that you could potentially memorize if you wanted. Make sense? Okay. So we've got some quick examples here. Spend some time, see what you can come up with. We'll do them in about a minute. So we'll address real quickly as we wind this up. I noticed a couple things while walking around. One, going back and referencing that previous slide where everything was like summarized, being like, okay, well, which does this match? Realize that is okay, but what you're pushing is a memorization, just so you're aware. Okay. The other thing that I saw was recognizing that we have a negative carbon and starting to do arrow pushing, which is fantastic. Okay, that's how I would argue that you should be doing it. If we go through and do that one, phenyl, because I'm lazy, there's our CH3, there's our O minus, step 2, H plus, add the H. Decent? Okay. Anybody think they got the second one? Going right to left? Yeah? Okay. This one I always have to check up on because I think I screwed this one up right here. And I forgot to check. The nitrile is just like a carbonyl. It can react the same. You can protonate. Be aware that the reagent conditions can make this a little bit trickier, so don't stress a lot about that because that's actually the next step or the next unit. Okay, and then this one, tack, break. Oops. I flipped it, which then makes it more difficult to track carbons. Whoops, come on. NH2, CH3. This last one, actually wrong. It is not NH2. NH3 plus. Okay? So I will attempt to real quickly talk about why that is NH3 plus. I'll try and verify this reaction because I don't remember if it stops once or if it does it twice. I think it does it twice. You should be able to tell me why CH4. And then for this weird carboxylic acid, in my walk around, I saw one person draw out the most important aspect of this. CO2 is a formula. You should turn it into a structure. And when you turn it into a structure, what do you see? You see your carbonyl that can potentially react. There's the result. Okay. With that, we'll go ahead and end.